Hey class, and welcome back. We're now going to talk about lab number 5, where we're going to do some investigations and some experiments with the idea of conservation of energy. An amazing concept that applies all around the world and in so many different aspects of physics. So in this lab, there's 3 parts to the lab. The first 2 are really kind of experiments that we're going to be doing, and the third is actually an analysis of data to look at conservation of energy. So it's going to be done primarily just through the computer, through Excel or Google Sheets. Some of the equipment you're going to need. For part 1, you're going to need one of your force sensors, probably the 5 or 10 Newton force meters that you have. You're going to need some sort of a spring, something like this that's relatively loose, or a rubber band. I have a few, here's a rubber band here. This is one I actually stole off of my projectile launcher, my slingshot. I also found this rubber band. It's a pretty firm, pretty stiff one. It doesn't stretch very long. This one's not going to work. It's actually too stiff. I'll show you that here in a minute. But that's what you need for part A of the lab. For part B, you need 3 different kind of sports balls, something smaller, maybe a ping pong ball or golf ball, and then a couple larger ones. I would actually, if you have one, go all the way up to something like a basketball or a soccer ball. But because I'm doing this in front of my computer, I'm not going to use a large ball like my basketball or soccer ball or something. But you need 3 different balls that you're going to be dropping from a height of 1 meter, which I'll show you here in a little bit. So if we talk about and look at the lab for a moment, there's pre-lab questions as always, so you have to think about and analyze some of these ideas ahead of time, preparing your ideas, thinking about the force exerted by a spring, the work done by a spring, and other concepts of conservation of energy. A great example that comes through a roller coaster. So for part A, you're going to be looking at the work done by a spring, it says, but again, if you don't have a spring, a rubber band will work. So what's the setup going to be? I'll show you in a second, but before I do, well, yeah, here, I'll go ahead and show you the setup, and then I want to talk about this. But keep in mind in this table here, you're only filling in the white squares. So you're going to fill in here, and here, and here. All the grayed out ones are places you don't enter something. Okay, so if you notice, you're going to find the force at a distance of 0 will be 0 newtons. Then the force required to stretch to 0.05 newtons, and then you're going to enter the average between those two. So the average force during the 0 to 0.5 centimeter distance you'll enter here. And then you'll record at 0.05 and at 0.1, recording the average in this square, and so on. So let me show you how you're going to do this. I'm going to tilt this away from my face into my desk. So here I have set up my ruler. I'm going to get the metric side over here. So I have my 0 centimeter mark right at this end. Okay. And what I'm going to do is I'm going to take either my spring or one of my rubber bands. All right. Again, you can do either one. And you want it kind of held loosely. Let's shift everything over just a little bit here. So you want it to where the end of the rubber band or spring is right at the end of your meter stick. And you're going to need to hold the other end firm so that it doesn't move. So I'm just going to hold it right here without moving it. You're going to then hook your force sensor onto this, again, keeping it at 0. So this is going to read 0 newtons when there's 0 stretch here. And then you're going to start to stretch it. It tells you to stretch first to 5 centimeters. Notice I'm stretching the very end of my spring from here to the 5 centimeter mark. So it's right at that 5 centimeter mark. And I would record the force to stretch at 5 centimeters. Then I'd stretch it to the 10 centimeter mark, recording the new force. 15 centimeters, recording the new force. 20 and 25 all the way. Since this is a relatively stretchy spring, you might have something that's a bit stiffer. So like I grabbed my wife's hairband here. This is like a rubber band. If you notice this guy, I tried to stretch this thing 5 centimeters and I can't. I can only stretch it like 2 or 3 centimeters before this thing maxes out. So in order to deal with something a little stiffer, you might need to go to a stronger force sensor. So this is one that goes up to 10 newtons instead. If I hook this guy on here, again, that's the 0 point. I stretch it. Now this one, I can get, oh boy howdy. So I could get this one, it'll max out at right around 8.5 centimeters. So instead of going 0, 5, 10, 25, and so on, I might go like 0, 1.5, 3, 4.5, 6, and 7.5 or something, right? So again, I'd stretch it to 1.5, measure the force. Stretch it to 3, measure the force. Stretch it to 4.5, measure the force. Stretch it to 6, measure the force. Stretch it to 7.5, measure the force. Okay, so if you do that, just keep in mind, right, you're going to have to edit your table. So for my spring or for my looser rubber band, I can leave it just as it is. Maybe I'd measure, all right, this took, 0.50 newtons to stretch it 5 centimeters. And then to stretch it 10 centimeters, it took 1.2 newtons. To stretch it 1.5, again, I'm just making up these numbers, this would be 2.5 or something like that. You'd fill that out for all of these values, and then this here where it says the average force, this would be the average between these two. So you add them up, 0.05 plus 0 divided by 2 would just be 0.25. Come down here, and this is now the average between the next two values. So 1.2 plus 0.5 is 1.7. Take the average of that, it's going to be, oh boy howdy, mental math, 0.85 I think. And same thing here, 1.5 plus 1.2 is going to, or sorry, 2.5 plus 1.2 is going to give you 3.7. So here you would put half of 3.7, which would be 1.85, I believe. All right, and so that's what you're doing. These are the average of these two values. And then you'll calculate the work, because work is force times displacement. So you'll take this, multiply by this, and enter that value right here, and do that all the way down. Okay? Keeping in mind now, if you switch to something like my wife's hair tie here, which is quite a bit stiffer, then you're going to need to change this, right? I changed this to 0.015 for each one of these steps. And then I'd have to go over here and change this. So this was 0.015, this was 0.03, this was 0.045, this would have been 0.6, and so on. I lost a 0 here. And this would be 0.075. So that's what would happen if I had a stiffer spring. And then again, I'd be using the stronger force sensor. All right, so that's what you're going to be doing on this part. As you can see, there's analysis where you then put this in data into Excel or Google Sheets. You plot it, get a linear fit, and other things to answer some of your post-lab questions and compare that to your pre-lab answers. All right, so that's the first part. The second part now is we're looking at how much energy is conserved or lost when dropping a ball. If you notice, if I take my bouncy ball here, drop it just off the desk in front of me, I dropped it from this height, but it only bounced back to about here. So it started with this much gravitational potential energy. It turned into kinetic energy just before hitting, right? It went from a certain height, and then it got faster and faster, turning into kinetic energy just before it hit. It hit, bounced off, and came up once again with kinetic energy because it was moving with a velocity, but its returning kinetic energy was less than its starting. It only bounced to a certain height. And that's because each different object is going to lose a certain amount of energy as a result of its collision with the table. I mean, just the simple fact that I can hear the ball bouncing means energy is being lost to the environment. It's taking energy away to vibrate the air so that I can hear it. So that ball is losing energy as a result of the impact. And so that's what we're going to be looking at in this part. So you're going to be taking each of your objects and you're going to be dropping them from a height of 1 meter and recording how far they bounce back up. So to do this, you need to get a situation like I have here. I have my meter stick here lined up against the wall. You might want to tape it to the wall or something. You might not have a meter stick like I do. I know not everybody can be this cool, but you might have a tape measure or something else that you can connect to the wall. Kind of zoom out. So if we kind of zoom out there, now we can see the full 1 meter. And what you're going to do then is you're going to take your various different objects, you're going to hold them at a height of 1 meter, release it, and see how far it bounces back. Now it's a little hard to tell how far it bounces back. It seems like it's around in here. So what I'm going to do, and what I'm going to encourage you all to do, is after you drop it a few times, get an idea of where it's going to land, I'm going to then actually make a video on my phone, go on here, centering it right around where I think it's going to go, start my video, drop the ball, and then use the video to see where it returned to. So apparently I didn't start the video on time. That went well. Let's try that again. So again, getting the video approximately where I think it needs to, putting the bottom of the ball at the top of the meter stick. Actually start my video this time. Let it bounce. So now I can go look at my video and watch it slowly bounce back and try to see exactly where it ends up. So again, I kind of get it right when it's at its maximum spot. Right at its maximum spot there, and it looks like the bottom of the ball is pretty much right in line with the 49 centimeter mark. So what I would put as my height that the ball returned to would be 0.49 meters. So again, it says ping pong ball here. I'd have to change this to my plastic ball or whatever I want to call it. And that first trial, it bounced back to 0.49 meters from where it started. And so I do it 3 times, switch balls, and do the same game. And then that's the data you'll collect. And then there's some post-lab questions here based on the masses. You're going to do some calculations about the energy. How much potential energy did it start with? How much kinetic energy did it have down at the bottom? And so on. Okay? And then, as I mentioned in the very last part, part C, you're actually just using data that I give you and doing some basic analysis. So you're going to be using these values here to calculate things like the velocity, the kinetic energy, the potential energy. Again, using our basic equations, all right? So you're going to be finding the delta V between different spots, as this equation tells you. So again, that's just looking at distance over time between these different values. You're going to be using distance over time to get the velocity. It's going to be negative because the ball is dropping. And then you use that velocity to calculate kinetic energy, and then you use the height to calculate the potential energy. And we'll see how the total energy changes as the ball falls. In theory, it should stay approximately the same, right? So keep that in mind. All right, so go ahead, try out lab number 5, and let me know if you have any questions. Have a Foxworthy day. Oh, yeah.